Well, welcome everyone to this SoC panel on serverless computing. This is, in my opinion, the most exciting future of cloud computing is serverless computing. So I'm super excited we have this excellent panel of 4 panelists here today to talk about it. Each panelist is going to give sort of a 4 to 6 minute opening remarks, and then we're going to open it up to questions. So I think if there's questions, just put them in the chat, or oh, someone says recording started. Should I hit record?
No, it's already recorded.
It's taken out of record. Okay, great. So if you have a question, please put it in the chat or raise your hand. We can call on you. But why don't we start off with our first panelist, who is Anna Klimovich. Anna is an assistant professor in computer science at ETH in Zurich. Before that, she was a research scientist at Google Brain, and she completed her PhD here at Stanford, where she worked on cloud storage systems. Anna.
Great, thank you. Can everyone see my screen?
Yes.
Okay. Perfect. So I thought I'd start by sharing kind of what I personally find particularly exciting about serverless computing. And the first thing is that by serverless computing, we're making it easier for people who are non-experts, or not computer systems experts, to leverage the scalability and elasticity of the cloud. So for me, functions as a service or serverless computing is one example of a broader trend in cloud computing about raising the level of abstraction for users so that users don't need to think in terms of virtual machines and fixed ratios of resources, but instead, whether it's functions as a service or data processing as a service, ML as a service, users kind of have this higher level interface to the cloud. And the cloud really is this pool of compute, memory, storage, networking that the provider stitches together the resources appropriate for particular jobs and sends users the bill for the amount of resources used. So I think this is exciting, this idea of raising the level of abstraction and making it easier to use the cloud. And then the other thing that I'm particularly excited about regarding serverless computing is the opportunity to improve resource efficiency. So to enable kind of, now that we have more responsibility for scheduling resources as a cloud provider, then we have more opportunity to, and we also have finer units of scheduling because of the small nature of these serverless tasks. There's an opportunity to do more efficient packing and scheduling of applications, and also to do so based on spare capacity, as Ricardo mentioned in the keynote. Basically using Slack resources to schedule serverless tasks because of their nature of being kind of limited in size, limited in their resource footprint, stateless, and so on. These are all useful properties, actually, if you are to schedule these functions. So in terms of challenges and opportunities for serverless computing, again, I think these fall into 2 broad categories, just like Ricardo also said in his keynote. Some are about broadening the scope or basically adding features to serverless computing to support a wider range of applications. And then another axis is improving the efficiency so that the actual resource utilization is improved. So regarding challenges and opportunities, one of these is providing quality of service. So today on these serverless computing platforms, there's not really a notion of performance guarantees that you get. But if you want to provide user-facing business-critical applications, it's useful to be able to express what kind of latency throughput guarantees you want, for example, and have the option of paying extra to get better predictability. But this is challenging to implement because we're talking about high degrees of multi-tenancy and resource allocations that need to be made at fine granularity and high rates. And another kind of area of challenges and opportunities is supporting diverse communication primitives. So today, kind of the main way to share state between serverless tasks is through remote storage. And one option for improving performance of jobs is to implement faster remote storage, and this was a direction that I worked on myself. But I also think it's important to support other communication primitives and basically optimize for locality when you can. So implementing direct communication between lambdas. And one option is to kind of try to expose this to users. This kind of might conflict with trying to raise the level of abstraction, make it easy to use. So another option is for the cloud provider to actually provide these primitives for communicating, but kind of abstract their implementation and just under the hood support locality aware scheduling and you can implement this point-to-point communication through a remote storage system, or message passing, or through a coordination server, or if things are running on the same machine, you can pass data directly. And then, to support more applications, stateful computation can also, basically attaching state to a function will let you support a wider range of applications that require this to run efficiently. And if I have one more minute, I'll just wrap up. So another aspect, a few other notes on exciting directions. Clearly, I'm pretty excited about this since there's several points. But I think supporting heterogeneous hardware is also something that's missing in today's platforms. But this doesn't just mean accelerators. I think this also means supporting diverse ratios of resources. So instead of kind of just having one knob to tune, like how much memory you want and everything being allocated in proportion, I think kind of the fact that cloud providers have a chance to, each function is registered by a user and then invoked potentially several times. There's an opportunity here for cloud providers to kind of adapt the resource allocation policy as they learn more about the utilization behavior of functions, and basically adjust the resource ratio and quantity to what that application might need. And finally, opportunistic computing is this idea that we can actually schedule serverless tasks to fill in the gaps that exist when you're kind of, if you think of an analogy of kind of rocks in a jar, you have these large scale services that you need to provide high performance for, but to kind of get better efficiency, you can fill in the spare capacity with serverless tasks. So I think this is another area of potential future work. Thanks, and I'll pass it on to the next panelist.
Thank you, Anna. That's really exciting stuff. Okay, well, let's go on to our next panelist, who is Sajjad Fouladi. Sajjad is a final year PhD student here at Stanford. He was the creator of the X camera and the GG systems, both of which kind of pioneered this idea of using serverless computing in burst parallel mode, firing up 10,000 cores for a task only when the user needs them. Sajjad.
Thank you, Keith, for the introduction. Hello, everyone. So today I'm going to talk about a dream, and I think it's a common dream between many of us. Imagine in 2 to 5 years, when this COVID situation is resolved, you're sitting in a cafe, you're doing your work on your laptop, and for most of your work, your laptop is totally fine. It has enough RAM and CPU for you to write code, work on your video, work on a 3D scene, all those kind of stuff. But eventually you may want to do a task that takes more resources or more than just a few minutes to run. Let me give you some examples. For example, if you want to encode a video, after you made all your edits and everything, it can take a very long time. A 15-minute long 4K video can take 7 hours to just produce the final output. Compiling software is another example. If you're working on a large code base after you made some changes to your code and you want to recompile your code or rerun unit tests, it can take a very long time, and you have to just sit there and wait for that operation to finish. Or for example, a 3D artist who is working on a scene, they are changing the lights, they are working on geometry, adding objects, materials, and they want to see the output of their work. And sometimes they have to sit there for an hour just to see the final output. Like this image that you see here is rendered using 1,000 cores in form of EC2 machines, and it takes 45 minutes and costed around $100 to render. So the dream that I'm talking about is that you have your laptop, and you're doing your work, and at some point when you want to do these everyday tasks that take a very long amount of time, you borrow cores from the cloud. You borrow 10,000 cores from the cloud, this sea of infinite resources, do your task in a few seconds or a few minutes instead of hours. And after you're done, you give those resources back and return to your normal workflow. And we believe that with serverless computing, we have actually this great opportunity for this burst parallel applications, applications that need thousands of cores for a short amount of time. to run interactively. And serverless, we believe that it gives us this opportunity to explore a lot of different ideas in these areas and probably bring massive parallelism to applications that we never thought of before. For the past few years, I've worked on, our group worked on like several projects exploring this idea using serverless platforms to run massively parallel tasks. For example, we worked on the Xcanner project that was published at NSTI 17, and we managed to use 5,000 workers on AWS Lambda to do this video encoding task in just 2.5 minutes. Or for example, in our project GG, we use AWS Lambda for software compilation. Using 8,000 workers on Lambda, we can compile Chromium in just 18 minutes compared to like 15 hours on a single core machine. And in our current project for ray tracing, we are using 2,000 Lambda workers in the cloud to render this image, not in 45 minutes, but in just 2 minutes with about 1/10 of the original cost. Throughout all these projects, I think we faced basically 2 categories of challenges. The first category is that many of these conventional applications and conventional algorithms were not designed with massive parallelism in mind. You know, like for example, video encoding for a long time, it was seen to be doomed to be sequential, you know, and we had to go and work through these algorithms to find ways to actually make them parallel at this massive scale. And the second problem that I believe it proved to be even more difficult than the first challenge is the implementing and deploying these applications to the cloud. You know, yeah, serverless is great. You can just, you know, do an HTTP request, invoke a function, and can run your code. But building these massively parallel applications on top of these platforms, you have to overcome a lot of challenges. And usually the application logic, you have to commingle that with a lot of details about the execution. And you know, in these 3 applications that I just mentioned, we faced a variety of different challenges in these areas. For example, that ray tracing project that I showed you, the amount of data that you have to send between these Lambda workers is about like 2 terabytes for just one single task, you know, and handling that kind of information with the abstractions that we currently have in serverless is nearly impossible. So I think there are some questions to ask here. So if we are going to like think as serverless as this 10,000 core laptop that can get all these resources at any point we need, what are the right abstractions, low level and high level, for this system? And I think it would be nice if as a community, we can start thinking about an operating system that allows us to do all these sorts of applications on top of these serverless platforms. Thank you.
Thank you. All right, our third panelist is Neeraja Yatawadekar. She received her PhD in computer science from UC Berkeley, and she's currently a postdoc also here at Stanford. Welcome.
Hi, thank you, Keith. One second. Okay, there we go. Thank you, Keith, for that introduction. Hi, everyone. Today, the focus of our discussion is going to be serverless computing. What, as you can see, I call the next phase of cloud computing. I think since this morning, a lot has been said about what serverless computing is. So I'm not going to spend a lot of time talking about it. But I will just say one thing. It is much more than what FAS is, which is the compute component, function as a service. It also includes BaaS, the backend as a service. And it actually, what exciting thing about this is that it may not be what existing systems or existing industrial solutions claim or define it to be. It is all actually up to us to envision and make it into what it could be. I think that is how fertile this area is. It's an exciting time to work on this. Having said that, there are these three aspects, which are, I think, have been repeated as a theme across the talks. But these are the three characteristics or features that define what serverless is in my mind. First of all, hiding the abstraction of servers, right? The cloud computing simplified a lot of ops, but hiding these servers actually takes away the worry about managing, provisioning, reserving, configuring, patching, scaling, and isolating. All of those operations are taken away, making it really easy for users. Secondly, the users now have to pay for what they really use and not what they think their peak demand might be needing. This cost efficiency is really, really attractive for users. And generally, mostly because users do not have an idea of how to predict what the peak is going to be. And they are not wrong. The problem is really hard. And finally, the third thing is the ability to scale on demand, the scale up to potentially infinite amount of invocations in real time, and scaling down when to zero, potentially, when demands plummet. As we see, a lot is made easy for users at the cost of making it harder for providers. But it also comes with a silver lining. The providers now have a lot of control over their resources, provisioning, allocating, scheduling, that they can actually build tools in time to optimize their resource usage, which translates back into cost efficiency for users. So before I move on, there are these three characteristics actually give rise to three prominent challenges that I wanted to do a mapping for. So first of all, the hiding of servers abstraction brings in question what programming model or interface should there be? Because now if I'm not thinking about servers, I'm not talking about number of VMs or type of VMs or containers, but I'm talking about these functions. And now what should the interface be? Today it is either using one or less than one knobs, memory size. How do we come up with that? Should that be the interface? I'll talk more about that in a little bit. Secondly, even though the finer granularity is allowing us to pay for what we use and not for what we allocate, it is actually bringing in the challenge of observability, because now an application that was easy to reason about is getting split into multiple smaller functions, and they are running across different, potentially across different hosts, different VMs. And that might bring in other security related challenges also, because the side channel attacks become more prominent in that case. They may become. And the third aspect is of auto scaling. When we have to auto scale to potentially millions of invocations in real time, we have to take another look at resource allocation and scheduling. So it seems really hard to get serverless computing right? You also heard in Sajjad's talk how much work it was. So let us make it a bit more tractable to get a handle on what we can do to make progress towards that vision. Think of application-specific and general purpose as two categories of serverless computing. Application-specific abstractions solve a particular use case, and several of them actually exist as products today. For example, AWS Athena. It makes it fairly easy for users to write, that's not me, which makes it fairly easy for the users to write SQL-like queries for data-intensive applications, right? While if you ask about general purpose, they do not exist yet. Right? General purpose abstractions must work well in a broad variety of use cases, and they remain a key challenge. So what do we have today? We have, in existing solutions, we have cloud functions, some of those APIs and other managed services. But if I have to build applications, as Sajjad also alluded to, if I'm talking about, say, video processing, where a user specifies a pipeline or a DAG of operations, a directed acyclic graph or data flow, there is no way for me right now to directly base it on the existing systems. So there is a huge gap, which is the opportunities and challenges that Anna also mentioned, a lot of them. I will take example of some of the things that we have been working on at Stanford. Because in the interest of double-blindedness, I'm going to use anonymous names here. System X basically takes or works on video analytics, these pipelines, with performance guarantees, or allows users to specify what their performance targets are. So to make this application work, we had to build a lot of components in between to fill in this gap. We had to come up with a specification language that allows users to specify the DAG. We had to build resource allocation and scheduling mechanisms, which takes that into account in addition to just running functions as individual entities. And then different components, they can be analytics components or machine learning components. They can big time benefit from heterogeneity of resources. And for that, there is currently no support provided. So we had to build our own component for that also. So, and the story was not very different for machine learning inference, the other system Y that we have been working on. So the idea is if we take dominant applications and try to fill in this gap in a top-down manner from application to where serverless computing is, it actually helps us, first of all, bring these applications to these platforms. But in the other direction, it also helps us understand what needs to happen in a bottom-up manner. So the commonalities where this resource allocation and scheduling needed to be revisited. So I don't have the time to talk about this a lot, but we have been working on what should really be a practical way to schedule functions on serverless platforms. So since I don't have time, the punchline here is look at the characteristics, look at the characteristics of existing workloads in serverless, look at the current architecture, and ask fundamental questions that enable us to look at existing scheduling mechanisms and change them in a more systematic way. So in the interest of time, I'm going to just leave all of you with this slide, which talks about what opportunities are. And I think Anna really talked a lot about these. So state management, networking, and security have been talked about, not just in Anna's talk, but in like the 6:30 a.m. talk or 6:45 a.m. talk by Ricardo. I will only touch upon the middle two, the predictable performance and heterogeneity. Predictable performance has already been a challenge in cloud, but if we are talking about serverless computing, the finer granularity makes it even more challenging. There is more vagaries in performance. But I believe what is exciting for me particularly is that machine learning will play a significant role here because first of all, the environments are becoming more and more complex and heuristics are going to need help. But secondly, because of the finer granularity, there is a lot more data that is getting generated, which helps with the challenge of statistical sufficiency or the sample efficiency, which makes it more amenable to machine learning. Okay, with that, I'm going to stop here. Thank you.
Thank you. That was great. Our final panelist is Arjun Singhvi, who's a PhD student at the University of Wisconsin-Madison, working with Professor Aditya Kela. He's broadly interested in networking and systems research, and his recent work focused on serverless computing, RDMA, and data analytics. Arjun.
Thanks, Kate, for the introduction. Can you guys see my screen?
Yes.
Okay. Yeah, so I'll just keep it quick because I think a few of the points overlap with what's already been spoken. Right, so the first thing which I find interesting as an open challenge in the context of serverless computing is state management, but more crucially, how do you provide state management for demanding applications, which say have strict latency requirements? And this is hard to do in today's serverless platforms because the way state management is done today is that compute and storage is sort of physically decoupled. Your storage service is running somewhere else, and now you have to go over the network to actually go write your data. And if you have a latency sensitive application, then resorting to such an approach is not going to be viable. Moving on, the other challenge which comes to mind in the context of, again, performant applications is how do you ensure that there is performance sandbox management, right? Given the cold start latency, it can lead to high tail latencies, which again could be something which is not viable for latency sensitive applications. The key question here is how would a cloud provider actually do sandbox management such that the tail latency again does not become too much. And this is sort of tricky again because the cloud provider sure is responsible for provisioning resources, but it should do it in such a manner that it is still cost effective and viable. Like the operational costs need to be such that it meets their goals. So that is something which is going to be challenging, where you have to balance both performance, which the users want, and efficiency, which what the cloud providers are after. And lastly, again, because we are targeting performance sensitive applications, ensuring that there are performance SLAs which are offered and adhered to, which Anna spoke about, is something which would be required today, where it would need to stem down into how would you actually schedule incoming requests, and also how would you place sandboxes such that in the future requests can actually leverage them. Moving on, right, like one of the key dreams of serverless computing was that you have this huge monolithic application, and now you actually break it down into smaller chunks and you actually run them so that they can scale up and down independently. So there, I think one of the key pieces which is required is to have a performant orchestration service. And that today is missing because performance measurements of our studies have shown that today existing platforms such as say AWS Step Functions or other orchestration services have high performance overheads, which again are not viable for performance sensitive applications. And lastly, I think a key question which is remaining is how would you design a networking stack, or what are the networking primitives which you would offer in the world of serverless computing? Today, as Anna mentioned, functions cannot communicate directly with each other, right? So one open question here is that what are the primitives which you would want to expose? But more importantly, I think another important question here which needs to be looked into is at a slightly lower layer, like is per flow fairness the right thing to go after, or would you want to service one Lambda completely before you go ahead and service some other Lambda? Because as you're processing network traffic, users are still getting charged for it. So like, how would you go about scheduling and orchestrating network traffic is also something which I think would need to be looked at. With that, I think I would end. Yeah.
Thank you, Arjun. That was great. And thank you for your brevity.
Yeah.
I want to repay the favor and ask you the first question, Arjun, and then we can open it up. Everyone here today talked about the importance, but also the challenges of state management in this new world. And so I want to ask you, where do you think we're heading there? Like, what would a better system, what is the challenge for state management? And then what is the dream? What would it look like in a world where we've solved these challenges?
Yeah, so I think like when serverless computing started, right, the approach which they took was essentially make a function stateless, because that would make the auto scaling mechanism really simple, because you don't have to worry about state, right? So that's the primary reason why they went ahead with the stateless function abstraction. And as a result, state was stored in a physically different service, right? And I think that made sense when we were starting out with such a computing paradigm. But now if you want to cater to larger apps, larger class of applications where performance is critical, I think the future would be where you have a combination of both, where you have like physical co-location, right, where there is physical coupling of compute and storage where state is associated with the function, but also you probably write it back to the remote store. So sort of a caching hierarchy where the first hierarchy would be that it's a local cache, and then your remote storage service could be the actual durable cache. That's what I think the future of state management would be towards.
All right, great. Anyone else want to chime in?
Sure. Anna, are you going? Okay.
Go ahead.
Okay. I only wanted to add to that. I mean, and I'm going to contradict to myself, but the state management actually can help a lot, can get help from a lot of hints from users, but that sort of goes against the vein of serverless computing and the thing that we keep saying, that users hardly know a lot of these things. So I don't know how to do that, but one way is to then allow the providers to infer those things over time. So there should be a time when we wait the initialization period, and then we converge to something that we learn about these applications, and that drives the caching hierarchy, as Arjun was talking about.
Yeah, I agree in terms of the opportunity to learn over time. I also think it would be useful to kind of unify some of the APIs to make this simpler for both users and providers, so that users can kind of write their applications with common APIs for communication, and under the hood, these can be implemented through storage systems, or if there's an opportunity to co-schedule or co-locate data and compute, then this can be done under the hood by the provider and kind of as a performance optimization, but without requiring changes to the user's application.
Okay, great. Let me ask the next question then about efficiency while I'm trying to learn how to get to this Hoover site. Anna, maybe could you tell us a little bit, what are the challenges and sort of opportunities for running serverless computing on, as you described, in an efficient way on sort of Slack resources?
Sure. So I think one of the things that I found interesting about serverless computing is that despite having kind of a lot of constraints in the programming model, like the fact that these functions have a limited runtime, and like execution time, there's a limited size for the executable, there's limited resource footprint. It's clear that there's been a lot of excitement about serverless computing, and the platforms, even as they are today, have addressed real use cases for applications like IoT, web microservices, and so on. But all of these kind of constraints that are part of serverless computing functions today, I think make it easier for cloud providers to schedule these resources. And open the door to scheduling on spare capacity. So to me, it still amazes me that in the cloud, it's very common to operate at 50% or lower utilization for the servers. And to me, that's a huge opportunity to improve resource efficiency. I mean, that slack is there for a reason. You need to, you have unanticipated load spikes, and you need to you need to have extra capacity to spill into. But what I think would be interesting, and I think serverless computing could be one of the ways of going forward, is to use that capacity temporarily, as long as you're willing to kind of relinquish your resources and able to relinquish resources quickly, and then kind of restart or rerun somewhere else. So I think the fact that with serverless computing, it's the provider who's doing the scheduling, and the fact that there's these constraints on applications, these make it kind of a simpler case. But one thing that I think we would really need here is, instead of kind of the failure or resource revocation being directly exposed to users, like it would be if you had an evictable VM, for example, then this is kind of not a good user experience if you're just kicked off your resources because you were running on Slack. Then I think instead what we need is application frameworks that are going to automatically reschedule jobs and decide where is the optimal way and to schedule jobs so that you can minimize the number of resource revocations that happen.
Oh, that's great. And some of you talked about the programming model. Like how, Sajid, or any of you, do you have any idea, how would we need to program these machines differently if we wanted to allow the provider to exploit that?
I think that's a very important question. I mean, our experience in building these applications was that the current programming interface that we get to these platforms is not at all efficient. And when you're, in case of like these burst parallel applications, when you're dealing with thousands and thousands of Lambda functions running in parallel, it's very even difficult to use the abstractions that we have in high-level programming languages like threads and locks and semaphores and those kind of things. So I kind of think that here there is this opportunity to bring some ideas from, for example, like the graphics community. They have this application like Halide, where the application logic and the patterns of memory access and data access are separate from each other. And so if we can, because for many of these applications, the logic sometimes is actually much simpler than the data patterns and data movement between these moving pieces. So one great opportunity that I see here is to basically start separating these two, the application logic from like a data movement patterns, and developing like separate program languages for describing each.
Can I add to that real brief?
Please.
Okay, because this is a little bit different from what Sajjad has been talking about. I fundamentally believe that the interface between the users and the providers needs to change in a way that the knowledge transfer can happen while maintaining the serverless benefits. The user shouldn't have to worry about it, but should still enable providers who already have a lot of data now, but still lack the, particularly legacy applications, or what is running inside those functions may not always be feasible for them to look into. So what can we do to change that abstraction, change that interface between them, allowing this flow of knowledge to transfer from users to providers so that they can actually make useful policies out of that? That's a big question. I think we all need to think about.
That's great. Let me transition. I really like this question from Tamer Oju, who asks, by the time you add state management and more sophisticated provisioning and orchestration and allow users richer APIs to configure more knobs and incorporate more communication, including interfunction communication, what remains of serverless?
I can take this just to put my thoughts across. So I think, yeah, so yeah, that's true. Like if we just go ahead with, say, making it more generic and making it suitable to a lot of applications in the way that we require users to actually provide us sort of all the inputs, where it could just be like, okay, there are so many VMs being offered and now you want to select which particular VM you want. And we maybe moving towards that sort of a world, right? But I think what is particularly challenging here is essentially what that API needs to be. It should be something which is natural to the end user to think about, right? And not something which is more to do, say, from a like from an infrastructure management or something of that sort. So, so I think that particular thing is going to be challenging, where we still have to maintain that level of abstraction, but we also want more information from the end user. So I think that's an open question, and we have to be sure that the abstraction still remains intuitive so that it does have the benefits of serverless.
All right, let's move to one of the Hoover questions. Heiner Litz asks, cloud providers want balanced resource utilization. Okay, cloud providers want balanced resource utilization 24/7. How to support burst parallel apps with cost efficiency while lacking control over tenants?
Yeah, that's a very good question. When we talk to actually like these providers and ask them about these kind of tasks that we have, like they usually ask us like, oh, what is your function invocation rate per minute? And we say that for most of the time it's 0, but suddenly we may want to get access to 10,000 cores in a few seconds. So that's a very valid question. That's, I think, an important challenge that designing these kind of systems, they have to like consider. One thing that I can say here is that the cloud providers are actually, I think, in the best position to offer these services, because yes, it's true that they have to like be able to provide the capacity for these best parallel computes, but you can imagine that they have a lot of customers, and they have like this opportunity to allocate a lot of resources that can basically keep them always busy by distributing these resources to different customers. So I don't really see that as a threat. I see that as actually as more like an opportunity for the cloud providers to offer these services and keep the resources busy and attract more customers.
Yeah, Roger, you unmuted yourself, but the next question would be for you too, but go for it if you want.
Oh, I just wanted to add to that. Statistical multiplexing or economies of the scale has always been what cloud computing is about. It has to be on demand and everything. And as I said, there is a long way to go. But if we want to support this real auto scaling, scaling to infinite capacity up and down to 0 also, it's going to take us more to take more fundamental look at those decade-long studied problems like scheduling, resource allocation, in addition to building these interfaces to make it work so that the servers are actually packed. But this is a very interesting question. These are contradicting goals, and that is why I think the cost right now doesn't actually really realize the promise, the cost efficiency, as even Gigi also talks about. I think Pyron also talks about. But once we get there, the hope is this would actually benefit both the cloud providers, because the resources will be utilized much more optimally, and that will translate into the cost efficiency for users also.
Well, here's a related question I thought was very perceptive from Chan Li, who asks, regarding QoS and SLA, besides execution latency and throughput, do you think there should be some unique requirements for serverless computing? For example, performance predictability.
So I think latency and throughput tend to be the easiest for users to think about when they want to translate on what that means for their application. But these actually might be kind of difficult SLOs for cloud providers to provide guarantees on directly, and it might actually other types of kind of QoS requirements I can imagine is sort of time to spin up the function, or kind of breaking down or sort of QoS in terms of how much concurrency you can have, or sort of what share of the resources on a machine you get, which I think are still useful, but sometimes I think latency and throughput are sort of the most easy for the user perspective to reason about. But it's quite possible that we might see some other QoS guarantees that are kind of more related to the infrastructure.
I can again briefly add. Absolutely. I think performance predictability should be made into the first class citizen that Chien is asking about. While that is true, and I agree completely with that, the question starts with how do you define it? Does predictability mean you run it multiple times and there is reproducibility in terms of performance? Even if that is the case, are you comparing it with native? What is that native? Do you have to isolate and run, and then that becomes your standard performance? And then based on that, everything changes. Then your pricing structure, it basically would be now comparing with that standard or that reference point that you had. So there are a bunch of challenges in getting it right. Given the complex environments, only adds to those challenges. But yes, I believe performance predictability will be required to actually finally be able to port latency critical applications to serverless.
Yeah, this is kind of interesting because before we talked about how there's an opportunity for cloud providers to observe a workload and adjust, like make optimizations in how they schedule things. So this can actually be like optimizing performance is a good thing, but if the goal is to kind of have predictable performance, meaning, and if that means that next time you run, you get the same performance, there's an interesting kind of tussle there of like, do you make these kind of adaptive policies that can lead to better performance, or do you prefer to just make things predictable and perhaps then easier to debug, or maybe, yeah, I'm sort of curious what users care about more. Is it the predictability or the raw performance? And I don't know.
Arjun, what do you think?
Yeah, I think just adding on, right? I think like the other thing which could be a metric which probably users could care about is like, say, the number of requests which incur cold starts, because that has a direct relation to the predictability with respect to the performance, right? So I think that could be something which is serverless specific, which is sort of becoming intuitive, because cold start is becoming is a huge problem, right? Which users are exposed to. So it's not something which is not totally non-intuitive, right? So I think that could be something which could be exposed as an SLA or QoS guarantee.
So that sort of segues into this nice question from Christina, who says that, prior work has shown the performance benefits of serverless for analytics and data parallel jobs. What do you think about the opportunities and challenges for serverless for interactive latency sensitive services? Arjun, why don't you, if you want to keep talking.
Yeah, I think it boils down to what are the contributors of latency, right? So there's the control plane and then there's the data plane, right? So in the context of data plane, it's the sandbox setup time and how much time it takes and how do you get around that? Like one solution could be that you proactively launch containers ahead of time based on the estimations of your resource workload, or the other thing is you reactively let requests come in and then you keep them around based on for however long you want to keep them around. So that sort of looks at the sandbox management and how much overhead do they incur in the critical part, right? The other thing I think, which I think deserves more attention than what it's got, is the control plane, which is essentially two aspects of it. Like one is the scheduling architecture and the other thing is the orchestration. Essentially will have impact on the performance guarantees of latency sensitive jobs as well, because if you have like say a centralized scheduler, it will give you a global view of your cluster, so you can make good scheduling decisions to say route your request to an existing container or sandbox which is already there, but it's not going to scale, right? And a decentralized scheduler is out there which can scale but does not have the global view. Right, so designing the ideal control plane architecture and a performant orchestrating service would become extremely critical in the context of latency sensitive applications. Yeah.
not to dampen that spirit, but preloading applications actually brings in how do you know when, right? And again, predicting in serverless manner has been, shown really, really hard. Unless it is timer based and it is pretty regular, you don't know what to bring in. So that might go back to using more memory and then just keeping
Yeah.
it the state. The other thing again ties it back to the interface. Again, through this interface, if we can maintain intuitive mechanisms where users can specify something more. Again, keeping it declarative though, not making them tell us exactly what should the providers do, but what they understand from high-level application logic. So there are a lot of challenges in actually reaching the latency sensitive applications being serverless. Great question, Christina.
All right, shall we move on? Here's a question from someone more general. From Preeti Murti asks, if I were to evaluate my application, if it's suitable to execute on a serverless platform, what are the set of factors to consider? Like maybe not every application is appropriate for this kind of model. Like what are the things to keep in mind?
Actually, I don't have an answer. I'm not answering, but I wanted to make this point specifically for Keith and Sajjad. I was listening to this talk by Tim Wagner in there is a serverless conference now, right? Which is right now predominantly industrial. But he was talking about, he was asked the same question, what should not be done on serverless platforms? And his answer was video transcoding. And then he was like, I was absolutely sure that nobody is going to stand there. No guy is going to stand there and going to say that, this is how I ran this on serverless and achieved this much benefits and whatnot. And then he basically shows X camera and says that I was happy to be proven wrong. So actually, it would be nice to hear from you when, it was pretty clear that this application was sort of not made for whatever state of serverless was. Why did you choose video transcoding going back? Keith or Sajjad, yeah.
Yeah, I think I can answer the question. Look, back then we were thinking about like building a video encoder that works across, thousands of threads. And serverless was just a means to an end. We just didn't want to, because like back then, like 4 years ago, you had to like pay for the full hour when you got an EC2 machine. But with serverless, it was just use that for the amount of time that you want and just pay for that amount of time. So for us, it was just a nice tool that you can launch 1,000 threads in just a few seconds and just run whatever C++ code that you have. If I want to go back to that question that like which applications are not right for serverless, it's a hard question to answer because like recently we made this ray tracer 3D renderer on top of AWS Lambda, and it's a crazy thing to do. It's I'm going to tell you why. Like these 3D scenes that we render, their size. So 3D rendering is highly parallelizable. It's embarrassingly parallel. It's basically simulating rays of light, and you can simulate each ray of light independent from all the other rays. So if you have 1 million cores, you can just trace each ray using a core completely in parallel. The problem is that the working set of each ray is actually gigabytes and gigabytes of data. Like a single ray can touch like 500 gigabytes of data. So imagine bringing that application into the serverless world where each of your workers, they have like 2 virtual CPUs and 3 gigabytes of RAM. Even if you can get like 1 million lambdas, they don't have enough memory capacity to actually carry on the embarrassingly parallel task that you're supposed to do. And what we found is that we have to like rethink that the way that we are thinking about parallelizing these applications. So even the like that task that we proved that like serverless could be a good fit to do this kind of task. And we did that by thinking about it in a different way. Instead of bringing data where the compute is, we basically distributed the scene into like a small parts among these workers, but then we had to like move all this data between these workers back and forth, like sometimes up to 1-2 terabyte of data that had to be streamed between all these workers. And at the end, it proved to be actually very, very useful, and we see a lot of like good benefits. So, we talk about like all these guarantees and all these features that we want for serverless. I kind of think that we may already have enough for a lot of applications. It's on the shoulders of application developers to like think of like new ways to bring their applications into this platform.
Let me ask all 4 panelists a very quick question, and then I'm going to move on to the next question, which will be for Anna. There's a lot of skepticism that we need some sort of direct network communication between these serverless workers. And Sajad has actually published that he's done direct network communication between Amazon Lambdas in Usenix. There seems to be a lot of skepticism about whether this is necessary. And even though you can technically do it, is it a good idea? And Rodrigo Fonseca asks, if you think of the decoupling of compute as storage, as a decoupling between compute and memory, do we really need direct communication? It brings back the duality between message passing and shared memory. Shouldn't it be possible to just maintain this decoupling, which has many advantages, and make it efficient? So I want to ask all 4 of you, do you think we're going to need some form of low latency communication between workers? Or can we maintain a decoupling between compute and storage and avoid any sort of low latency communication between workers? And I'd like a short answer, like a yes or a no. I think all 4 of you have maybe published in this area, and I think not in agreement. So I'm curious what you think.
Yeah, I can start a short answer. So I think there needs to be, there ideally needs to be direct communication between workers. Like just an example of an application which I would be presenting later on in the conference is network functions, right? Like they require ultra low latency in the microsecond, like order 10 microseconds or even lesser, right? So if you think of having a remote service, then it just adds this whole RTT and additional overhead. So I think there are applications out there which would probably require direct communication.
All right. Arjun says yes.
I would go next because I want to say no.
Okay.
I don't think a hard dependency on network communication is a good idea. The failure mode becomes hard. And short answer, so I'll just say a soft dependency, say a caching layer. If you don't find it locally, you'll find it somewhere else, and that will keep things in track. That's what I feel.
All right. 2 panelists remaining.
So I would say you can do a lot with remote storage and get pretty good performance. I think there are definitely some applications where to get the performance you would want or that would compare to non-serverless platforms, you would need direct communication. So it's also a question of what type of applications we want to support. But I think we can also distinguish between logical and physical disaggregation of compute and storage. And so even if the logical abstraction, I think, is useful in being able to allocate individually compute and storage is useful for flexibility, and physical co-location is often helpful for performance. So that's kind of a maybe, I guess. Depends which apps.
So I'm going to say yes, and I'm kind of want to dodge this question, but I would say that the programmer and the application developers, they are not the ones that should be worried about this. This is, I think, like message passing and shared memory, these are not the primitives that we want our programmers and application developers use as an API. But on the lower layer, on the infrastructure level, I think if we want to bring many future applications that support low latency execution, we are going to need this direct network communication, or at least like some sort of like low latency communication between the workers.
All right, great. Now, Rodrigo clarifies that he didn't preclude low latency when he talked about the disaggregated storage. I apologize for butchering the question. let's move on. Here's a question for Anna Klimovich, which is, and maybe the rest of you can chime in after she answers it, but what should be the next step for a serverless ephemeral storage system, such as Pocket? Do we need to add fault tolerance or quality of service, or what is the next step for serverless ephemeral storage?
Right. So for the question of, okay, since you brought up fault tolerance, I would say that sort of, I think in the application framework is where I see that fault tolerance belongs. I think it's an important part of the story, but I think the ephemeral store itself is dealing with ephemeral data and can be designed simpler and more efficiently when it doesn't have to replicate data or have erasure coding. So in my opinion, fault tolerance can kind of be managed at more of an application level. One of the things that I think is interesting for one of the directions that we were thinking about with Pocket as ephemeral storage as a future step is running it on Slack resources, actually, because you have you can kind of use serverless computing maybe to fill in spare gaps of compute. It's perhaps even harder to fill spare gaps of storage, and this kind of temporary data is perhaps a good fit to fill in gaps of spare compute. That's kind of from a cloud provider perspective, and from a user perspective, yeah, I think it's still an open question how, I mean, we don't have QoS guarantees for serverless computing in general. So I think that would be a first step, but then translating how QoS at the storage layer fits in with end-to-end QoS for serverless apps is another interesting question.
All right. Let's see. Nikhil asks, porting serverless computing ideas to the edge may not be viable now because of high latency. How can we change the serverless idea to cater to the edge? This might be an Arjun question, but all of you should feel free to chime in.
Yeah, I think it sort of goes back to Christina's question, right? Like where you have low latency interactive applications. So you would need to make sure that the latency contributors in the critical part do not show up that often, be it the sandbox management or the control plane latency. So that's what I would put it across as. But then again, it becomes challenging because if you want to, it's hard, like Neil was saying, it's hard to predict the resource, the arrival patterns of these requests ahead of time. So it might be challenging in that context.
Anyone else want to talk about the edge?
I would just say this, I think, depends a lot on the application, because I don't want to say the privacy concerns are what govern the edge applications, because then otherwise that includes all of IoT. But depending on the application and the requirements, some of the things can be done, because the latency is a challenge for every latency critical application as it is for the edge. So it depends on the application.
All right, great. Let's close with a forward-looking question from Preeti Murthy, who asks, it seems targeting a wide range of applications in terms of different factors that all the speakers mentioned is an endless challenge. Where do you stop?
Okay, maybe I can just get us started. Where do we stop? I think, as I said in my short intro also, there is a lot of benefit in looking at dominant applications and filling in that gap where we are and what applications really need. In my own experience, looking at it that way has actually helped understand what needs to be done from bottom up. But thinking directly from bottom to these applications is very hard. Once you actually dive deeper into an individual application, understand the patterns, and then think of similarities of that application with other applications, helps you sort of crystallize what components need work. And you go on adding that, and the bottom layer starts scrolling up and starts filling that gap. So I don't have a quantitative answer to saying that, okay, you have looked at 10 different applications that span the space or anything. But, you know, when when you have figured out what those boxes are and they are open enough in terms of incorporating all these different application types, when there is much small amount of work required when you want to use something, port something to serverless, that's when you stop. But where that point is very hard to say at this point, in my opinion.
Yeah, there was a related question about like how do you need to support all Linux system calls? For example, what are the OS requirements for fast systems? I think one of the interesting things is that you don't necessarily, it's hard to know what users will use your platform for. And so it is useful to have all kinds of different features, but also see which ones get picked up and used, and where do people kind of run into issues, and what parts need more work. So I think it's very much kind of a conversation between users and cloud providers. And we might see the focus change based on kind of how the users and applications they're developing are driving things.
Yeah, I think just adding on to that, right? Like when serverless came out, like the function lifetime was just 60 seconds, right? And then it moved on to 5 minutes, and now it's like 15 minutes. So I think this constant evolution based on what the users want and what the providers can support, I think that's something which will continue going on.
Sada, did you want to answer that question?
I mean, I personally don't want to stop, but I think there is still a lot to squeeze from these services, even in their current shape, with their current features and their current limitations. So I think there is still a lot to explore.
Okay. Well, thank you all for joining us, and thank you to the attendees for those excellent questions. I thought we had a great panel. The future apparently is bright. Thank you all. I think we're out of time, so we'll go on to the next session. Bye.
Thank you, Keith.
Thank you all.
Bye, everyone.
Thank you.